Hello, everybody. We are the University at Buffalo Engineers for a Sustainable World Solar District Cup team, and we're here today to present to you our optimization strategy for Ball State University. So this is the structure of our team. We had 8 members working on this, including freshmen and sophomores of a variety of engineering majors. And so we began together with a preliminary assessment of the site provided to us. We want to look for all the available roof and ground spaces. And afterwards, we examined the master plan of BSU. Then we separated into 4 different sub-teams, did our own research and design on Aurora Solar. And then afterwards, we came together, we looked at all of our designs and compared them. And then we finally picked one that was optimal for our final design. So this is our final design. This is just a map of the BSU campus and that northern section of land. And so we will have solar systems in these 4 locations, totaling to an installed PV of 2.5 megawatts and a total energy offset of 26.5%, which was calculated with the consumption data provided to us.
This is our proposed 100 kilowatt installation on the architecture building, which is located at the heart of Ball State's campus. We feel this could be a great marquee system for the university, and that it could show the current campus community, the surrounding community, as well as prospective students, just how much Ball State holds sustainability at its core values. The architecture building curtain wall is south-facing, making it ideal for a PV system. We propose putting the panels flush against the curtain wall surface to minimize mounting costs and allow them to be naturally washed. And we were also careful to leave about a meter's worth of space between each horizontal row of panels to still allow for sufficient daylighting into the building. This is our proposed system on the Neuer complex, a residence hall. And we'd like to point out that we were careful to only place panels where there was solar access of 95% or greater in order to prevent cumulative losses due to shading in the strings. This is our proposed 0.5 megawatt system on the parking garage. The pros of this system is that you don't have to worry about drilling into water lines or other risks you would have with putting PV on academic buildings, nor covering up green space as you would get with a ground mount system. And we have half of the panels facing east, half facing west, so that this PV would have max output at different times of the day than our other south-facing installations. This is our last and largest proposed system, a 1.2 megawatt ground mount system, which would be on the northwestern extent of Ball State's campus, but still very much a part of the campus community, as you can see based on the student apartment complex to the right of the system. This is a great open space to pack a lot of power and to also put such a large battery that we're proposing. It's also removed from the hub of campus in case there was any electrical failure associated with the equipment. Our final proposed VA price to Ball State is 11 cents per kilowatt hour with an escalation rate of 2.5% per year, slightly higher than our assumed inflation rate of 2% when we were modeling. And though we acknowledge that this is a little on the high side for a PPA price, we believe the other benefits of our system would outweigh the costs. This is a graphic showing our value stacking strategy. Since Ball State is charged based on the peak 15-minute integrated consumption interval for each month, a peak shaving strategy is best. And you can see in blue where the battery would discharge, and in red where the PV would serve the load, mainly between the hours of 10 a.m. and 5 p.m. To offset that peak demand. And then in orange where the PV would charge the battery on those days where the total consumption is lower, also represented in the dashed line, which shows the state of charge of the battery. Now we'd like to go into some of the details of our different deliverable sections, starting with the conceptual system design. These are our 3 different equipment specifications for panel, inverter, and battery pack. We chose the QPeak Duo 430 watt panel due to its high efficiency and power rating. And we chose a 30 kilowatt, 230 volt inverter from SunGrow. Because it has such a high power and also has 2 maximum power point trackers, we were able to minimize the number of inverters that we would need. Then we chose Tesla's Megapack for the battery, which is ideal for utility scale solutions. And we would only need 2 of these 3 megawatt hour batteries to reach our proposed 6 megawatt hour capacity. Now we'd like to highlight some of our tactics we employed when stringing. On the top left, you can see one of the 70 arrays that comprised our ground mount system. And in the top right is a snippet from one of our single line diagrams. These in general show our strategy to combine 10 panels together in series, and then 4 of these strings together in parallel to each inverter to get the most bang for our energy buck from each inverter. And in the graphic below, you can see how we strung panels from the bottom up on the architecture building to minimize the length of DC wiring needed and to minimize the number of inverters needed. For distribution system impact analysis, we used OpenDSS. These images show 2 types of plots out of the several different exports that we use to analyze after each iteration to make sure that any proposed systems would not cause an electrical violation within the system. The top left is a voltage distance plot, and in the top right is a voltage heat map. And you can see those are for the circuit as given without any changes. And in the bottom, you can clearly see what happens with a voltage violation, as is what happened when I incorrectly assigned the primary voltage to the system. The voltages jump way outside of the allowed ANSI ranges, and the heat map goes completely red. And now in the top right is a power plot with the line width representing power density. You can see in the bottom right how we had to add in a line to extend over to the ground mount system. And then this is an example of our sensitivity analysis that we performed. In the left, you can see when we added a transformer at the ground mount system, the voltage jumps way up in that line as expected, as well as the power, which ultimately led to a current overload in the transformer. For financial analysis, we use the provided financial model from the HeatSpring Solar MBA course. And this diagram shows the array of inputs that we had to use, including in the top left, our PV system size considerations from Aurora, our utility charge information from our tariff rate book, capital costs and financing structure information based on national benchmarks and averages, tax burden and incentive information, and most importantly, our PPA price and escalator. This table here shows an example of the iteration that we performed within our financial model. With the columns on the left with the same PPA price, you can see as the PV size increases from left to right in the top row that the NPV and IRR also increased. And with our final proposed size of 2.5 megawatts on the right, we played around with the PPA price to first find where the NPV was positive and we met our investors' target IRR. And on the rightmost column highlighted in yellow, where we could finally get the cash flow to be positive in each year of the 20-year investment. Then we used REOpt Lite, which suggested to us the best battery size and dispatch strategy based on finances and a desired resiliency premium. On the left, we were recommended a 1 kilowatt PV, 3 kilowatt hour battery size with no size constraints, which shows just how difficult the rate structure that we were working within was. And then when we then specified the 2.5 megawatts, we got a much larger battery. We wanted to see what happened with a resiliency premium. And through our research, we were surprised to find that Indiana is part of the US Census region that has the highest average power outage duration in the country, based mainly on severe weather incidents like tornadoes and thunderstorms. And then we analyzed Energy Information Administration reports and found that since 2013, Central Indiana has had 6 major outages ranging from 10 hours to 72 hours, depending on the utility. So we inputted an arbitrary average outage length of 38 hours into REOpt Lite to find that we would need a whopping 8.6 megawatt and 16 megawatt hour PV and battery size to support 50% of Ball State's load during an outage of this duration. Taking all this into account, we decided on a battery size of 0.75 megawatts and 6 megawatt hours. This sizing is more appropriate to the 1.2 ground mount system, 1.2 megawatt ground mount system that we were directly connecting it to. And it's on the high side of a discharge period, 8 hours of the battery's rated power, which shows our emphasis on resiliency. And we believe that this system would not only be able to offset a significant portion of Ball State's critical load during a outage, but that it could be an emergency shelter for the surrounding community as well. And we believe that if Ball State invests in this PV plus storage system, that it could be a national leader in sustainability and energy resiliency.
Now onto our development plan. For our development plan of our project, we had to focus and prioritize the following things listed here. So beginning with wanting to align with the master plan of BSU, including their visions and goals. Their master plan actually did revolve a lot around increasing their sustainability efforts, and they provided 3 possible ways of doing so by reducing their greenhouse gas emissions, increasing renewable energy sources, and developing on-site solar PV production systems. And fortunately, with our solar arrays, we'll be able to do all 3 of these things and therefore increase BSU sustainability. We also want to make sure we align with the goals of the Muncie District, and their district plan did mention wanting to increase nature conservation efforts and community attractiveness, which we'll get into in a bit. One of the major things we had to do was make sure that we did comply with all of the district zoning ordinances and any restrictions. So in the image to the right, taken from the Delaware County mapping tool, you see BSU and that northern section of land. And so you see that BSU is considered a resident zone 4 area, and that northern section is considered a resident zone 2 area. And so because they're classified in different zoning areas, we had to make sure we did follow the rules and restrictions of both an R2 and an R4 zone. We also had to make sure we took any potential risks and concern from the community members into consideration. And these risks included things like fire hazards, glare prevention, to even noise pollution. And lastly, we want to make sure that we gave the BSU community and the Muncie community an engaging experience with these panels. And this is where our ground system along the northern section of land comes into play. So this will be a walkthrough solar array exhibit. So it will be completely accessible to the public of both BSU and Muncie. People will be able to walk in between the panels, and there'll be signs along the way that have fun tidbits and interesting facts about solar and renewable energy. It will also have ways that people can incorporate solar energy into their daily lives, and ways that people can just reduce their daily energy consumption in general, which will hopefully encourage them to actually do so. There will also be vegetation around the perimeter of the land and benches and seating areas, as well as a mural hopefully painted by the community. Next slide. Okay. This is our construction timeline. It includes everything from the actual planning and conceptualization to the construction and end of it. And so the entire process will take approximately a year to complete, and the construction will take about 6 months to complete, and all these timestamps include any possible delays. Lastly, we want to be technologically innovative, as well as come up with innovative ways to engage the community. So we are using the acronym CORE to better explain our innovative strategies, and it stands for Cool, Optimize, Reduce, and Engage. So cool refers to the chimney effect, which is depicted in the image to the right. And so this is in regards to the curtain wall on the architecture building, which will work to cool the panels when they overheat. And then optimize just refers to what we did in our Aurora Solar design, where we tested all the tilt angles and orientations and other configurations and picked the most optimal one that maximized the amount of solar energy intake. And then reduce and engage just refers to that walkthrough solar array exhibit, which hopefully encourages BSU and the Muncie District to reduce their daily energy consumption while also giving them a fun and engaging experience. With that, I will conclude this presentation. Thank you for listening, and we're ready for questions.